My first lecture will be very different from the other one, and from my second lecture will be much more technical. In the sense, it will be less technical and much more focused on historical and conceptual major issues, because I want to give you an idea what is cosmology, where it comes from, what it tries to achieve, what were some of the major discoveries, what is the current status in observation, and so on, and what have been some of the, in my opinion, not so well justified criticism of the back sequence for the fundamental theories, and why we think within the next 50 years we might get to test in a stronger sense, in a Copernican sense, fundamental theories of frame such as string theory. To this point, the leading counter candidate, look point in gravity, not probably behind because nobody has a fully satisfactory solution of the issue of constraints. That's the name. But anyway, so this is the brief outline. Now, everybody should have seen this diagram. It's famous by now. It comes from okay, the last 10-15 years, ongoing revolution in cosmology, which came from precision measurements of the cosmic microwave background, which initiated the field of precision performance. And there's a lot more to come to improve this picture. So this is the basic history of the universe as we understand it until now. The age of the universe is estimated to have been about 13.8 billion years. This started in a hot Big Bang. We don't really understand the period exactly why it started, how it started, but that's where quantum gravity should be relevant, very relevant, fundamental. Then it went through a period of inflation, a very brief period of inflation, during which the universe expanded by a factor e to the power 50 or e to the power 60, so gigantic, extremely fast expansion. Okay. Then you have a number of stages. CP breaking stage, hadron formation stage, and so on, up to the recombination state when the cosmic microwave background was emitted to become radiation. And the number of later stages. So early universe cosmology refers to the period before decoupling of CMB. Okay? And very early universe cosmology, which is the focus of attempts to test fundamental theories of gravity and matter, refers to the period until the end of inflation. And of course, you want to push it as close to the Big Bang as possible to reach the Planck scale, which is the very beginning of inflation. So that's going to be a focus of attempts to test fundamental theories, the very, very early universe cosmology. Good. So, what is modern cosmology? Of course, there's the ancient cosmology. So this talk, the history of modern cosmology started with the discovery of cosmological solutions of Einstein's equations in general relativity. That happened at the beginning of the 20th century. Okay. Fundamental observation at the time was that the only smooth solution which obeys the cosmological principle. The cosmological principle is more of a philosophical origin. Assumption that we make. It states that the universe is spatially homogeneous and isotropic on very large scales relative to any observer. That comes from the idea that anywhere you look at the sky, from anywhere you are in the universe, it should be pretty much the same. It's a principle that you believe or not. Until now, assuming this principle, what we observe is compatible with most observation. And if you want to contradict that principle, you have to come up with a good reason why you should another discussion. There are no really good reasons why you should believe this. Good. So if you assume the cosmological principle, then you can show, and it's well known, that the only smooth solution which obeys it, the smooth solutions of Einstein's equations, is the so-called family, the only family of smooth solutions, the so-called family of FLRW spacetimes. So F stands for Friedmann, 1932 and 1904, two papers. Lemaitre was a principal in 1927, and then later Robertson and Walker. So this matrix, spacetime matrix in 4 dimensions, have a square line element in this form, minus d squared plus c square d sigma square, where I'm using the mostly plus convention, so the matrix has signature minus, comma, plus, plus, plus. Okay. And the matrix is written in so-called comoving coordinates. A is called the scale factor. It's a function, which is a function of a single real variable, which is positive everywhere. The single real variable is t, denoted by t, is called cosmological time. Okay, and this sigma square here is a square line element of a Riemannian metric of constant sectional curvature, which gives you the geometry of the spatial section, big sigma of the spaceline. And you can write metrics of this type in this form, again in comoving coordinates. Here R is a radial variable in the spatial directions. Theta and phi are angular variables on the two sphere. Okay. R theta phi, in which this d sigma square, the general Riemannian metric of constant sectional curvature in 3 dimensions can be written like this, are called reduced circumference spherical coordinates on the spatial section sigma. And kappa is the parameter which can be minus 1, 0, or 1. Okay. Minus 1 are the so-called open universes, 0 is the so-called flat universe, spatial. And 1 corresponds to the so-called closed universe. Okay. These coordinates cover only half of the 3 sphere when kappa is plus 1. When kappa is plus 1, the geometry is set of a 3 sphere divided possibly by the 3 group. Okay, that's the issue of cosmic topology, whether the discrete group is only or not. Okay, but of course you can use more than this. Very standard. So the topology of the spatial section, as I mentioned, is of the type sigma naught divided by gamma, where sigma naught is a 3 sphere R3 or H3, hyperbolic free space. Okay. These are the complete versions. Sigma naught is complete. Okay. Complete and simply connected. And gamma, which is in this case here should be a subgroup, not a moment, is a subgroup of the discrete subgroup of the group of isometries of sigma naught. Okay. Is allowed mathematically. Whether it is allowed by the observation data is an ongoing question. So there's a whole field of called cosmic topology, which tries to see to what extent the current data allows sigma to be mathematical. It's a ongoing question. To analyze the data from this point. So that project is run by the so-called compact collaboration. According to their analysis, which is rather recent, the last 2 years, it is not yet ruled out that this gamma, which is pi 1 sigma, will be complete. It's still allowed. Good. And of course, that comes just for the cosmological principle, but Einstein's equations impose some conditions. Okay. So Einstein's equations with the cosmological constant, and with the assumption that T mu nu, the stress energy tensor, is the most general one compatible with the cosmological principle, isotropy and homogeneity, space-like directions, at every point in the universe. So that principle forces the crystalline tensor to have formally the form of letter an ideal fluid, okay, the isotropic ideal fluid. So it can be brought, it can be diagonalized to this form. Okay, where rho corresponds to the pressure of the would-be fluid, and P corresponds to rho corresponds to the density, and P corresponds to the pressure. So the Einstein equations with the assumptions give the assumptions forced by the cosmological principle are equivalent to the following two equations written here. The dot represents a derivative with respect to cosmological time, and H is a logarithmic derivative with respect to cosmological time of the conformance factor AST. Okay? So this system of ODEs, there are ODEs for A, involving the density and pressure. Matter on considered a very large scale of the universe are equivalent to motion. The cosmological constant can be interpreted as dark energy. So dark energy is just a name for a would-be form of matter whose density and pressure are equal to minus lambda, respectively plus lambda, where lambda is the famous cosmological constant. Of course, with this formal definitions, the equations say that dark energy should be P lambda is equal to minus 1, which is rather weird. That's what comes from the good. So the case when A, the conformal factor is constant, with kappa is plus 1, close to the universe, gives the famous, historically famous, Einstein static universe, which is incompatible with the interpretation for a long time. It is not compatible. That's related historically to the so-called steady-state models proposed by Per Hoyle. They are certainly ruled out because we know for sure that the universe is currently expanding. This was an observation originally made by Hubble in 1929, and it's extremely well confirmed. The current version of the Hubble parameter, so at 0 indicates now the current time, is given here. It's about 67 to 70 inverse kilometers, inverse megaparsec. And of course, there is some issue about which of these two limits are actually the better approximation to the current version of the Hubble parameter. And that issue is known as Hubble tension. It's about comparing all the data, parallel observations using the old standard candles to newer data which come from the use of quasars and neutron stars. Good. So that takes you to the 1950s. Now, in between 1950 and 1966, there were new observations which increasingly supported the Big Bang theory. Just from this model, it is not entirely clear whether you have a universe which oscillates, whether there was an initial singulating in the past. Idea or what. But you have more and more observations about the far radiation sources, okay, which take you farther back in time, that was the earliest moment of the universe, which increasingly started to support hot Big Bang theory. This theory was already, this hypothesis, the Big Bang hypothesis, was originally proposed by Lemaitre and developed in the 50s and 60s by Calin. It was bitterly opposed by people like Calin, who were not really wrong. Just got wrong, despite being famous. Okay? There are still some diehards who try to disbelieve it using arguments initiated by Calin distinct, but I think the vast majority of people think that it's by now well established that the wider Big Bang. Okay? One of the most important discoveries during that time period, the 1950s and up to the mid-1960s, was the discovery of the cosmic microwave background. Okay, it's due to Penzias and Wilson in 1965. During the same period, there were theoretical developments which showed that the positivity conditions in general relativity imply that the universe must have a singularity in the past. It's a very important conceptually, and one of the main theoretical arguments against the following events. And of course, it's due to Hoffman-Ellis. First version in 1966, then much improved, in particular book, Hawking and Ellis and further papers and so on, and by many others. That singularity, of course, cannot be real. It comes from the fact that they use general relativity, which is classical theory, so it's supposed to be resolved by quantum gravity. The nature of those effects is still unknown. It's related to what your personal belief about what probability should be. Turns out to be. Now, in the late half of 1960s and then with many developments up to the early 1980s, we saw, due to the increasing conviction of people that the Big Bang idea is correct, the development of what later came to be known as the hot Big Bang model, a Vesper particle physics. This is pretty much the era of, during which what is now known as Vesper particle physics became established as a proper subject at the intersection between cosmology and astrophysics. So it's not a new thing, Vesper particle physics. It's just the fact that some people are unaware that it lost. It comes from that field. Good. So this included a number of important developments. The theory of nucleosynthesis. The main names there were Gamow, Walter, and Herman, which turned out to explain remarkably well the abundances of helium, deuterium, and lithium in the universe. There were many other people, theoretical developments, experimental confirmations, and so on, observational confirmations. So some important names there were Peebles, Fowler, Hoyle, in particular related to this abundance of black elements. Another important development was the theory of baryogenesis. There we have Sakharov, the same Sakharov who later became a designer, who also brought important contributions to Russian Soviet nuclear program. That's from 1967, certainly not new. And there was quite a bit of progress on understanding the cosmic microwave backgrounds. In particular, an important discovery of the period was that of the Fourier-Zeldovich effect, which is very important to take the effect into account in order to correct distortions induced in the microwave background by electron effects that will appear after the decoupling time, decoupling radiation from time. So that's from 1969. That effect was detected, confirmed in 1983. So there's been a lot of progress during that period. And then another very important development in the 1980s is the birth of early universe cosmology, very early universe cosmology. We start with the first models of inflation. That appeared with a very speculative paper of Alan Guth in 1980, and an attempt by Starobinsky in the same year to flesh it out by proposing some specific models, in particular the famous Lazaroiu. Okay. It was very controversial at the beginning. It wasn't well fleshed out, it's mostly an idea. There was very little observational confirmation, many theoretical issues were not understood, very speculative. But it gradually started to become less speculative because a lack of issues that had to be formulated properly theoretically started to be addressed. In particular, there were the first developments of cosmological perturbation theory, or what we now call one-field models, and then of models of structure formation, which is not related to inflation, but related to understanding the later period in the universe. However, it is very important for making sense of how structure in the universe is. The main idea was, and it's involved in this speculation, initial speculation about inflation, that very small fluctuations of the synchrotron field, or maybe more than one field, that happened in the very early stages of the universe during inflation, got frozen out because of this very fast expansion of the universe. And those microscopic fluctuations are ultimately responsible for the fluctuations that produce the large structure of the universe, which we now know to manifest in the formation of filaments, galaxies, and all this various structure, classical galaxies, similar to structure in the universe, all the way down to the level of galaxies, stars. So these primordial inhomogeneities had to somehow explain the formation of very large structure. And the very first models of large structure were proposing of how large structure may have appeared from such primordial fluctuations were proposed in the 1980s. In fact, the first computer simulations based on simple such models were done between 1983 and 1987. As early as that, imagine they didn't have a lot of computer power. The first space observatories of the Cosmological background also date from that period. In fact, the very first one was a Soviet one. It was called Relict 1. It was active between 1993. It was in space between 1983 and 1984. So again, it's more than 40 years. 40 years. It was followed by Kobe, which was mostly United States run satellite, which operated between 1989 and 1993. So that's the end of the Cold War period. Okay. When the whole, of course, rocket program of the Soviet Union, space program of the Soviet Union was frozen, it became bankrupt, it had to be saved, parts of it were saved by the United States, and that's why Russia, except for theoretical contribution, somehow disappears for a long time after that. Okay? And the US and Western Europe later was the European Space Agency take over the observation field. Okay? Also, the first models of cold dark matter date back to 1982. So none of these ideas are new. They go back a long time, and by now there's an awful lot of evidence. In those early days, there were little evidence, and the evidence started to refer. Good. Now we pass to the 1990s, which is 30 years ago. That was a period when what is now called the lambda CDM model, or standard model of cosmology, was developed. CDM stands for cold dark matter, lambda means cosmological. That was the period of the observation of cosmic microwave background anisotropy. There were already predictions of that from cosmological perturbation theory made almost 20 years before. So this is the confirmation of that, and the first detail measure of that. The discovery of the fact that in the current day, the universe is not only expand, but expand in an accelerated way, which means that the cosmological constant never be zero. That was due in the 1990s to the so-called supernova cosmology project and the HIZ supernova search. HIZ supernova search started in 1998. So the conclusion of that is a cosmological constant is positive, very small but positive, pretty positive. Also in the 90s, you had a confirmation of the first acoustic peak in the CMB, which had been predicted theoretically. And that is a confirmation of the phenomenon of baryon oscillations, which was part of the development in studying between the 60s and 70s. Okay. This is the boomerang in 1999. And also in the 90s, we had observational evidence of the fact that the spatial section of the universe is almost flat. So we are a very, very good approximation, which is kappa. So there was quite a lot to learn in the 90s. Then we passed to the 2000s. In that period, there were many refinements of the lambda CDM model, where the first large-scale numerical simulation of the structure formation, which confirmed the basic ideas of the lambda CDM model and primordial interpretation of the cosmological theory. So yes, structure formation works quite well, surprisingly well. Those ideas that were very speculative initially turned out to work well. There were further precision measurements of the CMB. Okay, that's the famous WMAP satellite, which was operational for between almost a decade, between 2001 and 2010. And also in the 2000s, early 2000s, first decade of the 2000s, we had the measurement of the E-mode polarization spectrum, the CMB. So this were DASI and CDI in 2004. Was further improved later. And in the second decade of the 2000s, there were higher precision measurements of the CMB from the Planck satellite of the European Space Agency that was operational between 2009 and 2013. And of course, the famous observation confirmation, first observation confirmation, strong observation confirmation, gravitation waves, due to the Lyman and Virgo observations in 2016. Okay, we are getting close to the pandemic here. We are approaching the present. And in the 2020s, of course, we have the James Webb Space Telescope, among many other projects, but that's already active. That started in 2021. So, quite a lot has been going on. If any of you are unaware, well, welcome to the So again, this is what we currently know reasonably well about the history of the universe. So you have the period before inflation, the Planck era, which is supposed to have lasted about 10 to minus 32 seconds. It's just to set the scales properly, to understand exactly what we're doing. It was followed by a cosmic inflation era. That's the origin of primordial fluctuations, which you ultimately got frozen in the form of large dispersion. That's crazy idea of structure formation, which is now works remarkably well. That's supposed to have lasted up between 10 to minus 32 seconds up to, depending on the model, around 10 to minus 30 seconds. Then you have this end of inflation period, okay, where the things that are settled down somewhere by radiating into extremely high energy particle, ultra-electric. So the first particles form, okay, after that. Then you have, I don't know, between 1 and 100 seconds after the start of the universe, formation of, beyond the formation of further particles, stage where ordinary matter particles are coupled to light, this very hot stage of the universe, and dark matter particles start building structures. This is also a period where we might have primordial black holes playing a role. Quite a few unknowns still there. Okay. Then you have the recombination era, which I mentioned, when electrons recombine with protons, forming hydrogen atoms. That's when the CMB, cosmological diagram of MET. And then you have later stages of it. Okay? So this gray part, which ends with the end of inflation, is the very early universe. This orange part, which contains all this particle physics story, which is now reasonably well understood, is the early universe. And everything late is called the later universe. So from recombination, which happened about 380,000 years after the Big Bang, to now, it's late universe. And that's the domain of mostly astrophysics rather than cosmology. It's that. So you want to test fundamental theories of quantum gravity, yeah, you have to aim for somewhere before 10 to minus 30 seconds. Delta. That tells you, well, it's not going to be easy. But it's not impossible. And it's certainly much better than trying at LHC. And you'll see in a moment why it's crazy to hope for progress in the LHC, because here you have energies which are more than 10 of the LHC. So cosmology is a much better chance to improve the energies. And even through cosmic radiation than from LHC. Or building higher. Yeah. That's why it's called the cosmology to actually test. Not from LHC. And that's why attacking string theory based on the lack of observation supersymmetry LHC is insane. It's unscientific. You are more than 10 orders of magnitude below the energy of the string theory supposed to be important. What do you want to claim? You make 10 orders of magnitude jump based on data. And also the claim that you'll never reach those energies is ridiculous because we have cosmology. We have extremely high energies in radiation and his years, cosmic radiation, much higher. Wait a moment. And before we bury the subject of quantum gravity and say that no young person should ever waste 1 second of his life, because some people have said something thinking about that, we should get in touch with this subject of cosmology and observation of cosmology for the past 100 years. Good. So this is a famous chart of Hilberian isotropies. Of course, things here are color-coded, and these fluctuations are extremely small, order of 10 to minus 5. But it's done in such a way that you can actually perceive them. So the isotropies are extremely small, which is consistent with the very strong analysis. Because otherwise it would be very hard to explain why they're that small. The is consistent with many physical instruction parameters. And since we got very close to the present, let's get into the deep present, the near and medium term future. What's actually going on? There's actually something very interesting going on in astronomy, sensual, which also includes observation and astrophysics. So anything that in that field, astronomy means you point something at the sky from the Earth or from a satellite or from the moon or from wherever. And you observe. Very general sense. Well, something very interesting that's been going on and is going on right now, likely to increase exponentially in the next 10 years. Namely, what is called the multi-messenger revolution in astronomy. Some of you might be unaware. It's a big thing. Okay. So the observation astronomy is currently in the beginning stages of the multi-messenger revolution. whose star can be dated back, if you want to be conventional, to the simultaneous observation of a neutron star merger on August 17, 2017. And 7 years ago. In the gravitational wave and extended electromagnetic spectrum by the LIGO-Virgo collaboration that relate to the same collaboration on gravitational waves. But that event was also simultaneously observed by about 100 electromagnetic spectrum observatories worldwide. And the data was collected, was analyzed using big data. So you can see that one thing that happened there is that you use more than one messenger. Okay? You use the electromagnetic spectrum and the gravitational wave spectrum. You use more than one observatory. And you combine the data. So you have multi-messenger observations, produce huge amounts of data. And you are able to analyze all of them together. So you have AI, neural networks involved, huge big data. You have multi-channel observations. And in particular, of course, the spectacular third eye, the IFIN-HH that we can actually see for the first time in gravitational wave spectrum. It's at the very beginning we can see only extremely special type of events in the spectrum, right? And you are, literally. And we are bound to learn something important from by using it. There are many arguments for why that will be looking. So what is multi-messenger astronomy? It's a nascent field of observational astronomy, which is defined by simultaneous and correlated observations of cosmic events and data, which use various information messengers available, namely all portions of the electromagnetic spectrum. So from microwaves and even longer wave ranges, all the way to hard X waves, extremely high frequency. You can combine observations such an extreme wide spectrum using computers, modern methods of data. But not only that, but also cosmic rays, which are another channel from which we can derive important information. Gravitational waves, and of course it's very difficult, but possible, neutrinos. So you already have quite a few channels, and you are able, for the first time in recent years, 7 or 8 years ago, to combine them productively and to pump that data for information. That's quite a big development. This is made possible by independent technological progress in each of these fields, but also by advances, as I mentioned, in computer networks and data analysis, which allow for real-time synchronization of detectors and for using machine learning techniques to analyze data. In particular, progress in neural networks enables processing of massive data produced by massive models. We have a combination, complex factors. This nascent field of observational astronomy holds great promise for the next 50 years, and pretty much with certainty will provide new information about the very early universe. What we crazy people who do these things here with all these speculations. For example, advanced gravitational wave detectors, which are going to be placed in space, narrowly practical in the direction, could provide information which is not easily visible in the cosmic microwave background, because the universe was opaque to electromagnetic radiation before the recombination phase. It's not that opaque to gravitational waves. We could see deeper into the past, closer, deeper into the inflation era, closer to the planet. So it's not crazy, not impossible, as some people have proposed to approach a point where you can actually test the real time. It's not impossible. It's alive. Gravitational wave astronomy is one of the most spectacular parts of this revolution. It is, of course, only in its nascent phase. The next step being discussed are projects such as LISA, which will probably be in space sometime after 2030. It's a project of the European Space Agency. Future generations of observatories hold substantial promise for the next half century. Next week. Okay. So to give you, convince you, it's not nonsense. It's not. I'm not going smoke to attend. Please here. This is from the website of the European Space Agency. It's about LISA, laser interferometer space antenna, which plans to put 3 satellites in space with large distances, about 2.5 million kilometers from each other, in order to increase precision of detection of gravitational waves, much weaker than those that were detected up to now. Hey, it will happen. It's approved, it is funded. It will happen. Hopefully by 2035. Good. Now, what is the truth about all this evil, incessant attack against any kind of person who tries to mention a word sincerely coming to one up? They should just shut up. They've been disproven by LHC. What do these LHC experiments show and what they actually do not show? What's the proof? First of all, of course, LHC experiments have found no evidence of supersymmetry up to energies of the order of 10 TeV. The highest collision energy attained at LHC in the current third run is about 13.6 tera electron volts. That's about 10 to 13 electron volts. Remember these numbers, it's very important. Orders of magnitude. The energy scale of inflation is around 10 to 13 tera electron volts, which is 10 to 25 electron volts. So that's from around 10 tera electron volts to 10 to 13 tera. To reach the energies of inflation, you are talking about 12 orders of magnitude above the LHC. Please anyone tell me if you consider that it's science to draw conclusions over 10 orders of magnitude in energy from experiments performed at LHC. I don't think that's science. Okay. Certainly Popper would consider that beyond unacceptable. Okay. But the Planck energy is about 1.2 times 10 to the 16 TeV, which is about 1.2 times 10 to 28 electron volts. That's about, sorry, 1,000 times, not 100. About 1,000 times the energy scale of inflation. So that's, only 15 orders of magnitude higher than LHC. But remarkably, it's only 3 orders of magnitude above the scale of inflation. So from inflationary physics, you can do precise observation of inflationary physics, which will be likely, especially with gravitational wave detectors and with some ongoing revolution in matter field astronomy. You could start to measure effects that were inherited from the Planck era. Wait. So we do have a chance in the next 50 years to draw conclusions. Our first conclusion about the Planck era. Experimental. No nonsense. Good. Good. So these are the energies that will be available. We are already drawing conclusions about energies of the order of the inflation scale, 10 to the 13 TeV. We have pretty reliable conclusions from cosmological perturbation theory, structure formation, and many other things. And we will be able to draw conclusions close to Planck. So no, I mean, fundamental physics is not bad. LHC didn't bury it. That's pseudoscience. Okay? So LHC energies, as I said, are 12 orders of magnitude below the energy scale of inflation and 15 orders of magnitude below the Planck. While LHC experiments practically do rule out certain models of low energy supersymmetry, such as the MSSM, which used to be the remaining clinical candidate. For those who don't know, MSSM is minimally supersymmetric standard model. It is impossible, logically, scientifically, and even commonsensically, to draw any conclusions about what happens at inflation of Planck's energy scales. You need a negative result of LHC. So you can vary things here. You can verify using LHC. Whoever claims that is lying, or just is so incompetent that he literally has no idea what physics is and what science is doing. So in particular, as I said, LHC experiments cannot invalidate superstring theory or supergravity, which are intended to describe the behavior of great wave matter at energies more than 10 orders of magnitude higher than those proper in LHC. I want to make a side remark about the ways in which naturalness arguments have been thoroughly misused, including by theorists which are known better. There's something called technical naturalness, which, frankly speaking, is nonsense, because you can't use naturalness arguments to put bounds on their coupling constant. You can only use them, and that was well known to talk to Wilson, who first made them, and so on. You can only use them to put bounds on the renormalized coupling constant. And of course, normalization has a renormalization scheme dependence. So such technical so-called naturalness arguments are empty. And they should never taken seriously. So however, an awful lot of the work, this even good now, is making claims about why you should have supersymmetry low energy scales, that you don't find it there, you shouldn't find it anywhere, and so on, were based on technical measurements, which is just wrong. Such arguments are certainly incompatible with Popper's epistemic standards for a theory of physics, which is even a greater attack, even if you disregard the fact that they are theoretical and nonsensical. That also naturalness is a philosophically weak idea. So I don't think that it should have ever been taken seriously in the past. You should keep that in mind when people start shouting, naturalness. No, naturalness is the God by far. It's not even clear whether we should care that much. Okay? Now, what we could actually learn from LHC about cosmology, very little about early universe cosmology. It might shed light on some aspects which are relevant to the post-inflationary era, so certainly not to the very early universe at such as quadron, blast, massive violation, precision measurements of cellular which of course are relevant to Western cosmology, some information about them. But it's very unlikely that we'll learn anything about the very early universe, inflation and before, from LHC. We have to look somewhere else. And to finish this, I want to make some maybe nasty, but I think necessary remarks on sociology, the internet, and the mass media. Everybody who has been working on mathematical aspects, fundamental theories of nature, knows that there's been an incessant assault against string theory and supergravity. Furious. It started about 5 years ago because of the negativity. The attack was mounted not only by certain scientists, but also through mass media, blogs, very YouTube influencers whose scientific credentials are doubtful, and everybody should be aware. The attack continues unabated. It is often characterized by the promotion of pseudoscience and even blatant nonsense, as anybody can check. Numerous false claims continue to be made regarding what LHC experiments supposedly show about what string theory supposedly states, which it doesn't actually states, and about the actual status of developments of alternative proposals, namely enormously inflated and false claims are made about what gravity is capable to state reliably. So, I think young people should be aware a systematic attempt is being made to mislead young people regarding the current status of scientific knowledge. Absurd denied statements and approaches are being presented as serious science, despite failing to test even the most basic common sense requirements of plausibility. The internet is full of this. That's not proper science. So, for young people, here are some common sense reminders. First of all, proper science is not done in the mass media, on blogs, YouTube, or TikTok, nor is it done in political fora, okay? But it's done through papers published in reputable scientific journals that are subject to rigorous peer review. This is how we do it. Okay? Second, internet influencers are unlikely to be competent in quantum gravity. That's not a subject that is easy to learn and understand properly. And third, it is not likely that naive ideas pushed by people whose mathematics background stops somewhere at the first or second year undergraduate will revolutionize that kind of subject. Okay, let's be silly. Good. So, as a counterpoint, rumors of my death, maybe the death string theory, or quantum gravity, will greatly exaggerate. And regarding this great look quantum gravity alternative string theory, you know, I will leave this as an open question for you, and you can try to check what is the actual status of this kind of gravity. The following questions, you know, does the proper quantum theory of canonical gravity actually exist? Because the quantum gravity is an approach to a form of canonical gravitation gravity rewriting the loop of the world. You know, what is quantum gravity anyway in the discourse of those people? Do they actually know exactly what they mean? You might want to consider this every time you encounter one of these claims. These are just questions, so I will just tell this a few words. So first, it should be the general education of the physics in the 21st century to read at least the book by Popper, Logic by Fortune, the Logic of Research, which is much richer than just what you read on Wikipedia. He was actually a very precise and cautious guy. In terms of, you know, just to understand what is supposed to be a testable theory, a falsifiable theory, a strongly falsifiable theory, a weakly falsifiable theory, what are the principles, the problems with natural induction. He does many, many things. And a lot of people who shout about Popper, like, look smarter than they are, have never actually read it. I think it's really a very good experience to read it and to compare it to, say, those algorithms that have been used in theoretical physics to have an idea of how we compare to those Popperian standards. Now, in my opinion, the only way to clean up is to try to be as close to those strong standards of Popper, the thickness, with the hierarchy, when we try to test fundamental theories. And I think that this is possible. I think that you are already gleaning from what I told you that it's not a crazy project, and that this is achievable. We can achieve something that's called effective testability, in my estimation, within the next 15 years, within the lifetime of the current humanity. You are going to be the first generation towards the end of your lives, when you are old, to see some proper tests in the Popperian sense. They can rule out, let's say, large classical string theory backgrounds, even other various ideas of quantum gravity. I think that you will live through it. So, you know, instead of listening to all these hysterics on the internet, mathematics and so on, you focus on trying to make progress with that area of science is not that. Good, time to test. Okay.